connecting a single-phase transformer to two phases of a three-phase 480-volt Y service should not present any operational issues. The 120 or 30-degree phase difference in the primary voltage sine wave between the two phases will not adversely affect the transformer's performance. The transformer is designed to function with a single-phase input. It will convert the input voltage to the specified output voltage, irrespective of the phase angle of the input. It's very important to correctly size the transformer for the intended load. An undersized transformer can overheat, which will lead to premature failure. Proper wiring is essential. Incorrect wiring can damage the transformer and any connected loads. When using a single-phase transformer with a three-phase input, there are a few guidelines. Firstly, the transformer must be rated for the voltage and current of the three-phase input. Secondly, the transformer must be correctly wired according to the manufacturer's instructions and all applicable electrical codes. Thirdly, the transformer's capacity must be adequate for the load it will supply. If the transformer is intended to power a motor, its rating must account for the motor's starting current, which can be significantly higher than its running current. Selecting the appropriate transformer involves several factors. Consider the voltage requirements. The transformer's primary voltage rating must match the available three-phase voltage, in this case, 480 volts. The secondary voltage rating must match the voltage required by the load, such as 240 volts or 120 volts. Next, consider the kVA rating. The transformer's kVA rating must be sufficient to handle the total load connected to it. Calculate the total kVA by summing the kVA of all individual loads. Add a safety margin of at least 25% to account for future load growth or unexpected surges. Wiring the transformer involves connecting the primary windings to the three-phase power source and the secondary windings to the load. Use appropriately sized conductors for all connections. Refer to the National Electrical Code, specifically Table 310.15b16, for guidance on conductor ampacity based on wire size, insulation type, and insulation method. Securely terminate all connections using appropriate connectors and terminals. Ground the transformer according to the NEC requirements. Proper grounding ensures safety and helps prevent electrical shock hazards. The NEC Article 250 covers grounding and bonding requirements. Overcurrent protection is essential to protect the transformer from overloads and short circuits. Install appropriately sized fuses or circuit breakers on both the primary and secondary sides of the transformer. The overcurrent protection devices should be sized according to the transformer's kVA rating and the NEC guidelines. Regularly inspect the transformer for signs of overheating, damage, or loose connections. Check the voltage and current levels to ensure they are within the transformer's rated limits. If any problems are detected, address them promptly to prevent further damage or safety hazards. Consider energy efficiency. When selecting a transformer, opt for energy-efficient models that meet or exceed industry standards such as Department of Energy efficiency requirements. Energy-efficient transformers reduce energy waste and lower operating costs. Also consider harmonics. Nonlinear loads such as electronic devices and some types of lighting can generate harmonic currents, which can cause overheating and other problems in transformers. If the load includes significant nonlinear components, consider using a transformer designed to mitigate harmonic effects or install harmonic filters. Furthermore, consider the ambient temperature. Transformers are typically rated for operation in specific ambient temperature ranges. If the transformer will be installed in an environment with high ambient temperatures, direct its kVA rating accordingly to prevent overheating. If the ambient temperature exceeds the transformer's rated limit, consider using a transformer with a higher temperature rating or providing additional cooling. Also consider the altitude. At higher altitudes, the air is less dense, which can reduce the transformer's cooling capacity. If the transformer will be installed at a high altitude, direct its kVA rating accordingly. You may also want to consider the enclosure type. Transformers are available in various enclosure types, such as open, ventilated, and enclosed. Select an enclosure type that is appropriate for the environment in which the transformer will be installed. For example, an enclosed transformer may be necessary in a dusty or corrosive environment. You should consider the insulation class. The transformer's insulation class indicates the maximum temperature that the insulation materials can withstand without degradation. Select an insulation class that is appropriate for the operating temperature of the transformer. Common insulation classes include 105 degrees Celsius, 130 degrees Celsius, 155 degrees Celsius, 180 degrees Celsius, and 220 degrees Celsius. Next, consider the impedance. The transformer's impedance affects the voltage regulation and short-circuit current. A higher impedance transformer will have better voltage regulation but will limit the short-circuit current. A lower impedance transformer will have poor voltage regulation but will allow a higher short-circuit current. Select an impedance that is appropriate for the application. And do not forget about the inrush current. When a transformer is energized, it can draw a high inrush current that can trip over current protection devices. Select overcurrent protection devices that are designed to withstand the inrush current. Also, you should consider the core material. The transformer's core material affects its efficiency and performance. Common core materials include silicon steel and amorphous metal. Amorphous metal cores are more efficient but are also more expensive. Also, you might want to consider the cooling method. Transformers are cooled by various methods such as air, oil, and water. Select a cooling method that is appropriate for the transformer size and application. Air-cooled transformers are typically used for smaller transformers, while oil-cooled and water-cooled transformers are used for larger transformers. You must also consider the noise level. Transformers can generate noise due to the vibration of the core and windings. If the transformer will be installed in a noise-sensitive area, select a transformer with a low noise level. Noise levels are typically measured in decibels. Additionally, always consult with a qualified electrician or engineer to ensure that the transformer is properly selected, installed, and maintained. They can provide valuable guidance and ensure compliance with all applicable electrical codes and safety standards. The purpose of a transformer is to transfer electrical energy from one circuit to another, typically to step up or step down voltage levels. Transformers operate on the principle of electromagnetic induction, where a changing magnetic field induces a voltage in a nearby coil. Key components of a transformer include the core, which provides a path for the magnetic flux, and the windings, which consist of coils of wire that carry the current. The primary winding is connected to the input voltage source, and the secondary winding is connected to the load. The ratio of the number of turns in the primary winding to the number of turns in the secondary winding determines the voltage transformation ratio. For example, a transformer with 21 turns in the primary winding and 1 turn in the secondary winding will step down the voltage by a factor of 21. The efficiency of a transformer is the ratio of the output power to the input power. Energy losses in a transformer occur due to factors such as core losses, hysteresis and eddy current losses, and copper losses, resistance losses in the windings. High-efficiency transformers minimize these losses to improve overall performance and reduce energy consumption. The impedance of a transformer is the opposition to the flow of alternating current. Transformer impedance is typically expressed as a percentage of the transformer's kV-ampere rating. The impedance affects the voltage regulation and short-circuit current. A higher impedance transformer will have better voltage regulation but will limit the short-circuit current. A lower impedance transformer will have poorer voltage regulation but will allow a higher short-circuit current. Voltage regulation is the change in secondary voltage from no load to full load, expressed as a percentage. A transformer with good voltage regulation will maintain a stable secondary voltage under varying load conditions. Short-circuit current is the current that flows through the transformer during a short-circuit condition. The short-circuit current is limited by the transformer's impedance. Overcurrent protection devices, such as fuses and circuit breakers, are used to protect the transformer from overcurrents and short circuits. Harmonics or sinusoidal voltages are currents that are integer multiples of the fundamental frequency. Nonlinear loads, such as electronic devices and some types of lighting, can generate harmonic currents, which can cause overheating and other problems in transformers. K-factor transformers are designed to mitigate the effects of harmonic currents. These transformers have a higher core loss and are designed to handle the additional heating caused by harmonic currents. The dielectric strength of a transformer is its ability to withstand high voltages without breakdown. Transformer insulation is designed to provide adequate dielectric strength to prevent short circuits and other insulation failures. Regular maintenance is essential to ensure the reliable operation of transformers. Maintenance tasks include inspecting the transformer for signs of damage, checking the oil level and condition, testing the insulation resistance, and tightening connections. Oil-filled transformers require periodic oil sampling and testing to ensure that the oil is free of contaminants and that it has adequate dielectric strength. Dry-type transformers do not require oil sampling or testing, but they should be inspected regularly for signs of dust or dirt accumulation. If a transformer fails, it is important to determine the cause of the failure before replacing it. Common causes of transformer failure include overloads, short circuits, insulation failures, and lightning strikes. Always follow safe work practices when working with transformers. To energize the transformer before performing any maintenance or repairs. Use appropriate personal protective equipment, such as gloves and safety glasses. Be aware of the hazards of working with electricity and take steps to prevent electrical shock. In summary, safely connecting a single-phase transformer to a three-phase supply requires careful consideration of factors such as voltage matching, kV-ampere rating, wiring practices, overcurrent protection, and grounding. Consulting with a qualified electrician or engineer is highly recommended to ensure a safe and reliable installation. Understanding transformer fundamentals, including electromagnetic induction, core and winding construction, voltage transformation, efficiency, impedance, voltage regulation, short-circuit current, harmonics, and maintenance practices is essential for working with transformers effectively and safely.